and welcome to the NPTEL online certification course on microelectronics devices to circuits. In our previous interactions we have seen that we have understood the basic concept of power dissipation, on what issues these power dissipations can be lowered, how can they be lowered. We also looked into the concept of delay, which means high to low and low to high propagation delay. We saw that the delay was obviously dependent on the width of the transistor, be it pull up or pull down, and therefore higher the width, lower was the value of your TPHL or TPLH. But the price you paid for it was that higher the width means more will be the capacitance, and therefore it will be difficult for the signal to drive the gate, right, because if your width increases, the area under the gate increases, and therefore that is the problem area. So, you need to optimize the design, and in one of the optimization problems which we saw in our previous case, we saw that if you are able to keep a fan out of approximately the stage ratio to approximately 3, we can get the minimum delay available to us. Keeping that in background, let us start with one module which is a critical module for estimating delay between point A and point B of a circuit, right, and that is what is the methodology which is adopted to do that is basically known as logical effort. So, the today's topic will be referred to as a logical effort. So, we will look at logical effort concept. So, what we will be doing is we will be introducing to you the logical effort, what is the basic I will give you the basic idea of logical effort and basic idea of logical effort. Then we will be coming to, so we will introduce to you the logical effort, what is the motivation for studying logical effort, and then what is the meaning of logical effort and where it is effectively used. So, basics of logical effort will be known to you. Then how to calculate logical effort for certain logic gates, right, and then look at the multi-stage network, and then we will finally recapitulate, right. Before we move forward, let me give you an idea about the concept, or let me give you an idea about how you design it. For example, if you have a gate which is something like this, which is basically a 2 input NAND gate, right, and you sometimes do like this, and then you do like this, then this is A and this is B. Then if you put A and B as your inputs, right, then you will see for 0 0, since both A and B is, so this is A, this is B. So, when both A and B are 0, output will be 1, when either one of them, these are still output will be 1, and when both are 1, output will be 0. So, this is your NAND gate approximation. So, A dot B bar, right. Now, the idea here is that you can only have one transition from so if you are storing 1 here, you can only go to 0 provided both A and B are equals to 1, which is this one. But you can, if this was initially 0, then you can go to 1 either of these 3. So, if you fall back to your previous understanding, you will know that, as I discussed with you, that 0 to 1 transitions are the transitions which are power consuming cycles. So, therefore, if the initially you have a data of 0 available with you, the probability that it will go to VDD is much higher as compared to it going to down, assuming that all the inputs are statistically possible and independent with respect to each other. Then if initially you had 0 in your V out output, then it can go to VDD only under all these 3 conditions, whereas it can stay to 0 only in one condition, which is basically this condition. So, you see that a power dissipation is therefore also depends upon the statistics of your input and the type of gate, whereas if you look at this point, and then if we, let us say, you design something like this, that now your pull up is basically series, right, and your pull down is basically in parallel. So, if you have A here and you have B here, so if you look here, then if you plot A, B and Y, Y is the output here, then if for this condition, right, when both are 0, then only you will have 1, for all other cases you will have 0, which means that you initially if you have 1 here, then the probability it to go to 0 is just that only one of the inputs or both of them should go to 1. So, the probability is just to go to 0 is much higher, whereas if it wants to go to 0, then both A and B has to go to 0. So, again I am assuming that if it is statistically independent and equal probability of getting all the signals are available with you, then I would not expect to see, I would expect to see power dissipating cycle more in a NOR 2 logic as compared to a NAND 2 logic. This is the first observation. The second observation is that you see when you are pulling up, you have 2 transistors in series, right, and when you are pulling down, in this case you have only even one transistor, if switches on you will be obviously in parallel. So, if we assume that each transistor has a resistance of R, then and if output is basically let us suppose is C, then I can safely say that if both the transistors are on, both will be in parallel, I will get tau equals to R by 2, right, into C. Whereas, if I assume this to be also R, this to be also R, then tau, this is tau P H L, right, and this is tau P L H will be equals to 2 R times C. So, means if I assume that NMOSes and PMOSes have exactly the same value of resistances being offered during the on state, then tau P H L is R C by 2, whereas tau P L H is 2 R C, right, and that is quite critical, that therefore, low to high propagation delay is 4 times larger as compared to high to low propagation delay. The same thing will reverse when you do a NAND 2 logic. This is for NOR 2 logic, this is for NOR 2 logic. For NAND, if you do a NAND 2 logic, for NAND 2 logic if you want to find out, then what will happen is that you will get an automatic reduction. So, tau P L H will be equals to 2 R C, and sorry, tau P L H will be equals to R C by 2, and tau P H L will be equals to R C, twice R C. I hope you understand the reason. So, therefore, if I in this case if I want to make that my high to low and low to high are equal, I need to size my PMOS in such a manner that my high to low and low to high are equal, right. So, they will be in series. So, if I am able to make this one R by 2 and this one R by 2, then even in series these two add up, you will get R only and they will make me equal. So, R by 2 primarily means that you make the width larger, but when you make the width larger, then this capacitive loading also increases drastically, right. So, this logical effort gives me an idea that what changes should I do in my circuitry in order to achieve the best possible results in terms of delay, right. With this basic introduction, let me introduce to you the topic which we were supposed to do. So, as I discussed with you that designing a circuit, that is what I was saying, that designing a circuit to achieve the greatest speed or minimum delay, it will give you large number of choices, right. So, you need to choose which is the best choice in front of you. Now, the idea is that therefore, how large should a logic gates transistor be to achieve the least delay. Please understand that just making it large does not make it achieve the least delay, because we just now saw that making it large also increase the capacitive loading, and therefore, your capacitive loading will be larger. Now, this is true for a single stage amplifier, but single stage design, but generally in today's world you have multi stage circuits, right. So, you have one stage driving another and so on and so forth. In such a scenario, if you look very carefully, the first stage is loaded by excessively by the subsequent stages. So, the subsequent stage's capacitive load will be so high that it will try to reduce the delay, try to enhance the delay of the first stage. So, can we therefore find out the total number of stages which gives you the minimum delay? So, what we say, the method of logical effort, if you look very carefully what is written here, then the method of logical effort is an easy way to minimize the delay in a logic circuit, right. So, what we do, we compare the delay estimates of different logic structures. For example, we compare for a NAND 2, NOR 2, XOR 2, and then we say that the fastest candidate can be given by this particular design. Logical effort also specifies the best number of stages in a logical path and the respective transistor sizes for a given load. So, which means that if I know for sure that my output load is CL or a load is given to me which is exactly equals to some load, then can we do a back calculation and say that okay, my transistor size should be this much for this much load to be driven by an input to get the minimum delay, right. So, the overall justification or overall idea is that given a set of choice or given a set of path or data path, can we in some way or other find out a methodology by which we can optimize the delay, right. So, this is what we get, right. Okay. So, two things which logical effort takes care of is what is the capacitive load, right. So, we have a you will have a delay because of capacitive load, right, and you also have a delay by virtue of the topology of the logic gate. This we were discussing in the starting slide, that there will be two delays associated with any design. The first delay will be the intrinsic delay, which is basically because of the device, because of the capacitances and so on and so forth, right. Whereas the second delay is basically depending upon the logic structure which you are using. Are you using a NAND to logic, are you using a NOR to logic, are you using what type of universal gate are you using in a digital logic in order to express it. Now, the absolute delay of a gate can be expressed as you can see is given by this basic formula, where D absolute is equals to D multiplied by tau. Now, D is basically a unitless delay of the gate and it depends upon the type of process through which you are designing that particular gate. So, this basically intrinsic delay, you cannot do too much manipulation in that, because it is basically depending on the type of process, the fabrication process through which the structure has gone through. So, typically for 0.6 micron technology, tau is approximately 50 picoseconds, and it is 12 picoseconds for 0.18 micron for 0.18 micron technology. And that is quite interesting, which means that as you go lower in the technology node, your intrinsic delay starts to lower down. So, you see a lowering down of intrinsic delay of 50 picosecond to 12 picosecond, right. Now, so why do you multiply both of them? The reason being that the reason you multiply is that tau is the delay unit. So, if tau is the delay unit, right, picosecond, if tau is 1 picosecond and D is the delay unit by virtue of the fabrication, we can actually find out the total delay to be equals to D into tau, right. Now, the delay of a logical gate D can be therefore broken up into two parts. One is known as a stage effort or a effort delay, and another is the parasitic delay. What is a parasitic delay? Well, parasitic delay is very simple, straightforward. We already discussed this point earlier also. Just to refresh your memories, I will just do it. Let us suppose you have a gate here, right, and you have a gate here, and you have a source and drain here, right. Now, what is happening is that the inversion layer is formed only below this region. So, this is where the inversion layer is formed, and you have large carrier concentration here. The resistivity here actually falls down. So, resistance is lowered much here. But you see, if you look at this region also as an underlap region, these two regions, right, this as well as this, then typically in these two regions you will automatically have a much higher delay, or the intrinsic delay will be larger, because there are no charge carriers here, and therefore this will act as a parasitic, which means that it is basically adding. So, so what will happen is something like this. It will be 1 R here corresponds to this, and then you have a straight wire, and then 1 R will be here. So, this is R1 and this is R2, or RS and RD. So, RSC, RDC, the parasitic. So, RSP and RDP. So, DP is the drain side parasitic and S is the source side parasitic, right. So, the delay is one delay will be by virtue of this, and you will also have a stage effort which is there. This stage effort has got two components, one is known as logical effort, another is known as electrical effort. Electrical effort is the most easiest one, H, and it is given as CL or C out by C in. So, let us suppose I have a buffer, or let me say a simple inverter, and if my output load capacitance is CL and my input load capacitance is C in, then CL this by this is effectively my H, right. This H is also sometimes referred to as fan out, right. So, this is also referred to as sometimes as fan out, right, C out and C in. Now, you can also have something like this, that you do have, let us suppose you have something like this, that let me say you have so you have, let us suppose, a buffer here, which means that you have, let us say, less. So, I will get 1 0 1 0, right, and I will just put a 0, I will get a 0. So, this is a buffer. Now, in the buffer, this is the load capacitance which you see, CL, external load, and this is my C in, right. So, C in. So, this by this is referred to as the electrical effort, fine. So, electrical effort is the, so higher the electrical effort, of course, as you can see, more will be the load capacitances compared to C in, and therefore, higher delay will be effectively large. So, F will be larger in that case if you get a higher electrical effort, right, and that is the problem area which people face as far as electrical effort is concerned. So, what is a logical effort? Logical effort tells you that of a logical gate, logical effort for a logical gate tells you how much worse it is at producing output current than an inverter, right. So, assuming that I have an inverter, I give an input to an inverter and I check out how much amount of current is flowing in the output side for a set of, for a pair of inputs. Then what I do, I take the same pair of input and put it into a logical gate to NAND, to whichever you want to calculate, and see how much current is flowing, right. If it is better, good, equal to an inverter, this logical effort will let me know, right. As we have already discussed, therefore, that logical gate, the delay in a logical gate will depend upon or will increase with the electrical effort. Obviously, it will do so. What is the electrical effort? Because H, right, higher the value of H you will have, higher will be the delay, and therefore, why? Because your loading is typically very large, right. And if you therefore see a plot between electrical effort and normalized delay, this graph here, you see you will have a parasitic delay P is a constant one, right. This is independent of number of inputs, number of gates, so on and so forth. It is basically process and device centric, and therefore, this parasitic delay is always constant, right. So, even when your electrical effort is 0, you still have some amount of normalized delay, for example, a 2 input NAND gate, right. We will talk about inverter later on. For example, a 2 input NAND gate, even with some electrical effort equals to 0, 0 means basically CL equals to 0. I will automatically have this 2, this 2 is because of primarily because of the parasitic delay which you see. Now, if you go on increasing the electrical effort, you automatically get a linear increase in the value of normalized delay, and this is true also because then your load in the external world is increasing, and therefore, your delay will go on increasing, right. We define therefore, in this case, so let us suppose we take an inverter which is a skewed inverter, then we define this to be as a parasitic delay, this P, and this F is my effort delay, this F is my effort delay. So, at about approximately 3, the value of your normalized delay is 4, and we define G as equals to 1 and H equals to P equals to 1. What is G and what is G? If you look back to your previous slide, G is this, which is basically my logical effort, right. So, G is my logical effort, and if you go back to your here, what is P? The P value is the parasitic delay. Parasitic delay is fixed, always fixed. So, I get F plus P equals to D, right. So, what I am doing here is that P is 1, see P is 1, right. What is G? Electrical effort is also, let us assume it to be 1, because for a inverter it is 1. Delay which you get capital D is equals to H plus 1, right. What is H? Is H is basically your electrical effort, and you get D equals to H plus 1, right. That is how you work out. And therefore, more complex logical gates have more logical effort. So, if you have got a, rather than a 2 input NAND gate, if you have a 3 input NAND gate, right, life becomes more difficult, and therefore, your logical effort is larger in that case, right, and you also have a larger parasitic delay for example, in that case, right. For example, if you look back here in a 2 input NAND gate, you see your parasitics are actually 2. This is parasitic for NAND gate. So, you see P equals to 2, right. we will see how why is it G equals to 4 by 3, but P equals to 2, right. The formula is G times right H plus the parasitic delay is your total delay. So, you see 4 into 3 into H plus 2, right, where H is the your electrical effort, right. So, if you are plotting here somewhere here, let us suppose you are plotting somewhere here, then here H equals to 3, 4 by 3 into 3 plus 2 is equal to 6. So, normalized delay is approximately equals to 6, fine. How we got 4 by 3 for G, we will see that just in the next subsequent slide. So, I get for 2 input NAND gate. Now, if it would have been more complex and let me say it would have been 2 input XOR gate, then the graph will change drastically in this case as compared to an inverter, right. Let me come to the next slide and let us see how a logical effort works out. Inverter logical effort, assuming that my input rise time and output fall time is exactly the same, I can write down input rise time is proportional to C out, which is this one, plus Cp. Cp is the loading capacitance which you see, which is given as beta times delay, right, beta times delay, or delay therefore can be written as beta times C out plus Cp. And if you plot C out plus Cp versus delay, you will always get a linear curve whose slope will be equals to beta. So, this is a standard way of looking at it. Now, how do you do a logical effort? You do it in this manner, that if you have a inverter which is basically a single input inverter, we make that PMOS is 2 times larger as compared to 1. So, that TPHL equal to TPLH. Now, we try to make a NOR 2 logic, a NAND 2 logic, and we have 2 PMOSs in parallel and 2 NMOSs in series. Now, if you want this delay to be exactly equals to this delay, you have to make the lower transistor size double, then only I will get R by 2 available to me. For pull up there is no issue, because pull up this is 2, for any 1 0 I get 2 here, and therefore, my pull up will be equal, but for pull down this is 1 and since this is 2, right. So, I need to so this is 1, so if I have to double it because it is in series. So, this will be R, if 1 corresponds to R, then 2 will corresponds to R by 2. So, R by 2 plus R by 2 is always equals to 2, and the pull down will be equal in that case. So, pull up and pull down will be again 2:1 available to you. So, you see in this case Cin is equal to 3. Why 3? Because 2 for PMOS and 1 for NMOS. Why is it 4 here? Because for single gate it is 2 for this thing and 2 for NMOS, right. So, we define G to be 4 by 3. 4 by 3 means 4 is the effective capacitance seen from the NAND 2 logic, right, divided by equally sized inverter which will give you the same delay. So, 4 by 3, right. For a NOR 2 logic things change slightly, and the reason is that they change slightly. Why? Because for NOR 2 logic, understand, if you want to compare this with this, then for pull down I can afford to be 1 because both are in parallel. So, each one of them is 1, no problem, but in the pull up I require this to be as 4, because then only it will become R by 2, because this is already 2. So, this has to be R by, to make it R by 2 I have to double the size. So, I am doubling the size. So, 4. So, 4 means each block is looking at 4 plus 1 5. So, 5 by 3 is basically my G, which you see, right. So, this is how you calculate the value of G, right. You compare that with a standalone inverter, right, and that is how you get it. So, if you look at some of the logical efforts and common gates, you see that inverter, which is basically the one input, obviously input has got only one for an inverter, parasitic delay is P inverter. For a NAND logic, for 2 input 4 by 3, 3 input 5. So, you see as the number of gates inputs increases, the logical effort also increases. The general formula is n plus 2 by 3 for NAND gate, and NOR gate it is 2n plus 1 by 3, where n is the number of inputs which you see, right, and that is a standard way of looking at it, or a way of looking at it. I will give an example of FO4 inverter delay, and if I have an inverter something like this, then F is equal to G into H. G, if you see single inverter is 1. So, 1 into, assuming that you are driving 4 such inverters. So, 1 into 4 is the output one. P inverter is the parasitic delay, assuming it to be equals to 1, I get D equals to F plus P inverter, right. F is nothing but 4. So, 4 plus 1 is 5, right. So, D absolute is equal to D into tau, typically as I discussed with you 12 picosecond for 180 nanometer. So, I get D absolute is equal to 5 into 12, which is 60 picoseconds. So, I got D from here, multiply that with 12, I get 60, which means that if I have a single transistor driving 4 similar transistors with fan out 4, I will get approximately 60 picosecond delay between the input and the output, right. Let us see an example of a NOR 2 logic. Let us suppose I have a single NOR 4 input NOR logic driving 10 such gates. So, as I discussed with you, F will be G into H, right. G in this case will be 9 by 3, right. It will be 9 by 3, you can check it for a 4 input NOR gate, for example. Just let me just show it to you. For a 4 input NAND gate, 4 2s are 8 plus 1 9 by 3, which you get, right, and that is what you get, 9 by 3 multiplied by 10, because equally sized. So, H will be equals to 10, right. So, I get and let us suppose the parasitic for inverter is 4. So, I get D equals to F plus inverter. So, I get 30, right, 30 plus 4 34, and for again 180 nanometer, 34 into 12 is 408 picosecond. So, therefore, a 4 input NOR driving 10 such 4 input NOR gate, the picosecond 408 picosecond is the gate. So, first you have to find out the F value, then you find out the if P parasitic is given to you, D equals to F plus P inverter. Once you find out the value of D, you then find out multiplied by tau. Tau is always fixed for a particular technology, and from there you can calculate the total delay between the gates. So, what we will try to do is give you a brief idea about the logical effort for a multi. So, path stage path. So, now if you have a large path, then what we do is that we define a path logical effort. So, in a large path we go on adding the logical effort for each one of them. We define path electrical effort as C out by C in, we have already discussed this path. We define a new term which is known as branching effort, which is C on path versus plus C off path by C on path, which means that let us suppose I have this and my signal goes via this path, then this is C off path and this is C on path. So, we see the C on path plus C off path divided by C on path gives you this value, and the total branching effort is given by this formula. From these explanations I get that total logical path will be Pi will be the individual stage. So, if you add all the individual stages you get the total branch effort. So, what you do is we define path effort to be equal to G B into H, right, and from there we find the delay as this plus P, which is P is the parasitic delay for each stage, right. We therefore say for an n stage network, stage effort for each stage will be f to the power 1 by n. So, we square root or nth root of f is my stage effort which we see, right. So, what we do is we define as n into f. So, n into nth root of f plus p is basically my delay, right, and that is what you get the total delay, minimum achievable delay along a path, right. So, the minimum capacitance seen at each stage will be given by this formula, where C in is basically the input capacitance of ith stage, and I get total in the output stage. For the ith stage I get C out divided by hi cap. Hi cap is the basically the logical effort, this f root n divided by logical effort, right. So, let me recapitulate. Therefore, if we have logical effort G, electrical effort as H, branching effort as B, then we define the total effort F is equal to G into H and effort delay to be equals to F and P, and therefore, the total delay is always equals to F plus P. How do you find out F? G into H you find out, right. So, in a single stage, so multiple stage you can do it. So, first of all find this and then you multiply with this and then you add to P and you get the total delay, right. So, we have understood two important points. I will come into details of this one at later course also, but at this stage we have actually understood that given, that means if a particular logic gate is driving some other logic gate, right, maybe it is a n input logic gate, we can find out the delay between point A and point B for the design, right. That will help you to gain in this area. With this, let me thank you for your hearing. Thanks a lot. Thank you.